I'd like to point out like a couple of sort of observations regarding the missing gravity problem in galaxies, this so-called flat outer rotation curves. Number one, we have dwarf galaxies as well, satellites of the Milky Way, but also field dwarfs, which are very poor in gas. They're mostly stars. They're also not rotating. They're supported by the random motions of the stars, so kind of like an elliptical galaxy. In fact, these are, if you like, dwarf elliptical galaxies. And the velocity dispersions in them are often much higher than you would get from applying Newtonian dynamics to the stars that we can see in them. There is missing gravity also in these non-rotating gas-poor systems, quite different to the rotating spiral galaxies like the Milky Way. So that's one thing. The other thing I'd like to point out is the gravity between the Milky Way and Andromeda galaxies must have been enough to turn their expansion around. And I don't know how you can, whether you can account for that, because there isn't. You're proposing that gravity is Newtonian, but there wouldn't be any long-range magnetic forces between them.
Well, I mean, the long and short of it is that, yeah, I haven't done any particular studies of the local group. The key point is that the vast majority of data on which is based the idea that dark matter has astronomical evidence for it. We're all agreed that there is enormous evidence against dark matter from the laboratory. But the idea that dark matter really has to exist and is not just a fudge comes from these rotation curves. That's the overwhelming amount of data. And what I'm saying is that data is overwhelmingly based on measurements of the motion of gas or plasma.
It's not entirely from the gas, though. I mean, if you also look at the orbital velocities of satellites around the Milky Way, and these are satellites which are mostly made of stars, or pretty much entirely made of stars, you can see the rotation curve of the Milky Way, for example, at 100 kiloparsec or 150 kiloparsec, is approximately the same as the velocity at which the sun orbits around the galactic center. It is true that astronomers generally consider the measurements based on the gas to be kind of more reliable, but there are data on the rotation speeds from stars as well, and they do show a flat rotation curve as well.
Right, but the question is, if you go out to larger and larger scales, then you have to take into account what is the actual balance between magnetic energy and gravitational energy.
I was just talking about the observations.
And in what?
I was just talking about the observed rotation speeds.
Yeah, but let me finish my answer, okay? What you have at many scales is that the controlling forces, the dominant energy, or at least equal energy, is in the form of magnetic fields. Those magnetic fields act directly on gas clouds. In many cases, those gas clouds are enormously more massive than the stars within them. So the motion of those gas clouds is controlled by both gravitation and magnetic field, and the stars within them are gravitationally bound to the gas clouds. So you can have the motion of stars indirectly controlled by the magnetic field. In a galaxy like the Milky Way, the stars in the inner part of the galaxy, where we're measuring velocities optically, the density of matter is too high for the magnetic fields to be controlling. A technical way of putting this is that the Alfvén velocity, which indicates how much energy you have in the magnetic field, is much lower than the actual velocity. But on many scales, and some even at the level of clusters of galaxies, That's not true. The Alfvén velocity exceeds the kinetic velocity, and there you have magnetic forces are powerful enough to control the motion of the clouds that the stars are embedded in. So you can have magnetic fields indirectly
So if I can,
controlling the mass of the clouds. By the way, the concept of mass density is quite critical to the behavior of these plasmas. And the graph I showed you, which was theoretically derived, gives a prediction for the mass density of the universe at large scales. And that prediction is very close to the observations of actual matter at these scales. One of the problems I have with the theories of some of my colleagues here is that they assume that the density of matter in the universe is the so-called closure density. And that closure density is about 100 times the density we actually observe.
Our videos come out of LPP Fusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description, and thanks.